curve cryptography. As we know, ECC was suggested independently by Neil Koblitz and Victor Miller in 1985, nothing less than 35 years ago. And after a long, windy, and at times bitter battle against RSA, ECC is now the undisputed most efficient, most effective, and most popular pre-quantum public key scheme around. And the main applications of ECC are on key exchange and digital signature protocols, and is used and deployed in massive applications such as OpenSSL, SSH, WhatsApp, crypto coins, you name it. There is a strong confidence in the classical hardness of the elliptic curve discrete log problem, ECDLP. Nevertheless, we know that ECC succumbs to Shor's algorithm implemented on large-scale quantum computers, which begs the question, how long can we safely use pre-quantum ECC? And thus the title of this panel. And we have plenty of additional discussion topics in this topic. So one question could be, can ECC be dead even before the arrival of quantum computers? Another, during the transition period, can possibly ECC coexist with post-quantum schemes for many years? And is there life for ECC after the arrival of quantum computers? What would be the cost in terms of qubits, T-gates, circuit depth of a quantum artifact that is able to break ECC? Or this one, what about this one? Which one will be broken first, RSA or ECC? And on a negative note, what if there is no major progress, say in the next 5 years? What is the probability that funding for quantum computing research will decline or even vanish? Is that a probability? Looking forward to an interesting and hopefully thought-provoking panel discussion. And just to start with the provocative questions, I would like to leave you with this one. Will ECC finally meet Dia de Muertos? Is that going to happen? So with that, I leave you, and now we will go with the presentation of our distinguished panelists. We have Michele Mosca, Manfred Lochta, and Sam Jacks. And we will ask the three of them to introduce themselves, and we will start with Michele. So Michele, could you please start?
So I'd like to introduce myself. I thought we were going to introduce each other. Did we change? Okay, I'll just introduce myself then. I'm Michele Mosca. I'm a mathematician at the University of Waterloo. I work in quantum computing and cryptography, both quantum algorithms, looking at the positive applications of quantum computing, but increasing attention to my original roots, which is in classical cryptanalysis of public key cryptography. So I'm very focused on the building blocks of making our digital systems secure against quantum attacks. I also started two companies, one in quantum safe cryptography and one in quantum software and applications.
Okay, thank you very much, Michele.
So then let me introduce myself. I'm Manfred Lochter from BSI Germany. BSI is a federal office for information security. When I started work, it was one of my tasks to introduce elliptic curves into government systems. And I'm, for example, behind the brain pool curves that some people like and others don't. Now things have changed a little bit, and my task is now to migrate to post-quantum cryptography. So at the moment we are mainly working on migration mechanisms towards post-quantum cryptography and also on quantum communication.
Thank you, Manfred. Sam, could you go ahead, please?
Hi, I'm Sam Jakes. So I'm a former student of Michele's, and I'm now a PhD student at the University of Oxford. And I've mainly looked at quantum cryptanalysis and cost models, in particular on elliptic curves and isogenies.
Okay, thank you very much to all of you. And according to the mechanics of this panel, I would like to ask you to briefly speak for maybe about 5 minutes on the general topic of this panel. How long can we safely use pre-quantum ECC? So we may start first with Michele. Michele, please.
Sure. And, the answer is it depends, like most questions in life. The first order depends on two things. How long do you need the information you're using to, that you're protecting with ECC? How long does that information need to remain confidential, say? We also can think about integrity, but let's just focus on confidentiality. So we call that X years, the security shelf life of the information. And then the other parameter, as I call it, is Z, the threat timeline. How many years before threat actors can start compromising the security of that information that you're protecting with ECC? And really you have Z minus X years where you're safe in a sense, right? You can keep using it for Z minus X years, and then, that information is going to have the X years of security that you need. Of course, we don't know Z, so then that's really the more subtle parameter is what's your comfort level or your risk comfort, right? Because if there's a small chance, of course, there's a small chance classically ECC is broken tomorrow. So, what's your risk tolerance, right? So then I guess we can get into the question of, what is Z? And again, we don't know certainly, but my own estimates the last year, which I updated at the ETSI ITC workshop, was a 20% chance of it happening in 10 years. I think for most people, that's too close for comfort, right? So I would strongly advise you treat Z as being less than 10. In fact, I think there's even a 1% chance in 5 years, right? And 1%, that's starting to get comparable, I think, to the chance that ECC gets broken classically over a decade period, say. So I would, depending on your risk tolerance, you probably want to have mitigations in place, again, assuming X is 0, even, in the next 5 to 10 years. And I guess I don't think it really matters from a risk management perspective, but I think for some people, they're really concerned about the other tail. I think the chance of it taking more than 20 years for quantum cryptanalysis is about 20%, sorry. So an 80% chance this is going to happen in the next 20 years. But I really think what matters the most is the beginning, the earlier part of that tail. And those are my own personal estimates based on a lot of analysis that I'll get into in a second, but we've also surveyed 22 thought leaders last year and asked them the same question, people building the computers, doing error correction, fault tolerance, optimizing algorithms and so on, and we produced a histogram of their estimates, which you can get for, it's available openly at the Global Risk Institute, and we're in the next few weeks, a short number of weeks, going to post the 2020 version of that survey where we interviewed 44 people. And you'll see my estimates are sort of middle of the pack. So, where do these estimates come from? Well, for me, first of all, I look at the opinions of these respected thought leaders and understand what they're thinking and saying, and the reasons for their arguments. I track circuit sizes. You optimize the algorithms at the top. You optimize the compilation of the algorithms. You look for breakthroughs in fault tolerance. You look for advances in the fidelities of the platforms, and you look for progress in the advancement of the platforms. The most critical milestone to first order, the question is how long before we achieve a logical qubit, and then how long will it take to scale it, right? That's sort of the supply side of the quantum tool, and in theory we're trying to reduce how many logical qubits we'll need, but we'll need logical qubits, right, as far as we know. So the biggest milestone is when to achieve fault tolerance. And, IBM says they're going to do it by 2023, and our survey that we're releasing in a few days, I think something like 30 out of the 44 respondents thought it was 50% likely. The choices were, less than 1%, less than 5%, less than 30%, about 50%, and greater than 70%, the reverse of those probabilities. And 30 out of 44 picked approximately 50% or the higher categories. So I think there's a serious likelihood of that fault tolerance milestone being achieved quite soon, right? In the next 3 to 5 years, say. Like a really high chance of that. And then it's a matter of how long will it take to scale. Of course, once that day happens, you don't really have much time to react, right? So you really have to be ready to hit the ground running before the fault tolerance milestone is achieved. And another factor that people often mention, there's this fantasy out there that, well, the first quantum computers, bad people won't have access to those, or bad people who I'm worried about won't have access to those. I wouldn't make that assumption. I'd give at most a 2-year buffer, if you want, to the time before the first quantum computer can do it versus adversaries you care about. And these are on the cloud. The commercial ones are on the cloud. And there is no way to keep bad people off the computing platform. Once it's available to good people in a commercial context, they're going to get on, right? So I wouldn't give yourself, there's no big safety buffer there, at least I wouldn't assume there is. And I guess the last closing comment I want to make, and I think we'll touch upon it later, but I think it's just so important, just because there's a chance ECC could, as you mentioned in your opening remarks, so first of all, you have to defend against all attacks. So the most widespread attack is, if you have access to a classical computer. So classical attacks, you don't have to hack into, some heavily protected quantum computer to do a classical attack, right? So you have to defend against classical attacks as well as quantum attacks. And ECC is, as you argued, and I believe it, our best defense against classical attacks for many years to come. And even then, even when we start to build up confidence in the post-quantum primitives, which I think will take a decade before it's comparable to ECC, there's still, one is not superseded by the other. Having both will provide you security, additional security against classical attacks until when? Well, until quantum computers are basically available for free to anybody, right? When you're close to that point, then there's really no additional value to ECC. Until that point, there's value. Of course, the value slowly diminishes, but there is value. So I personally wouldn't go out of my way to remove ECC from a system where it's already integrated unless there's a really good reason, because I think it does provide security. And so I'm sort of answering one of your other questions, but I just want to be clear, just because you should stop relying only on ECC in the short term, I do think we should keep using it for many decades.
Excellent opening remarks. Thank you very much, Michele. We go now with Manfred. Manfred, please.
Yes. 1 second. Am I unmuted? Yes.
Absolutely. Yeah.
So I will try to say the same things with different words. So the question is, how long can we safely use ECC? And this depends on many factors. One is, when will there be cryptographically relevant quantum computers? And even that's a complicated question, because you don't know how progress in algorithms is. We don't know which cryptographic attacks are possible with quantum computers today. People are concentrating on Shor and Grover, maybe HHL. But there are also examples where you can speed up traditional algorithms using quantum computers as a coprocessor. And as this is becoming a research topic, there may be progress that we don't expect at the moment, right? We are hearing Google and IBM talking about 1 million qubit quantum computer within 10 years. We have Michele's numbers, we have the BSI study. I think all are quite optimistic that there will be quantum computers anyway during the next decade, probably. And for BSI, this means we have a working hypothesis, and this is we assume that there will be relevant quantum computers in the 2030s, beginning of the 2030s. That doesn't mean that we are 100% sure. It just means we have done a risk assessment and that we feel it's necessary to act now. So the next question is, what are you using ECC for? There's a difference. If you use it for short-term signatures, like in TLS, you may have some years. If you use it for key agreement, situation is worse because you can do the store and decrypt later thing. And it's similar for, say, roots of PKIs with a long lifetime. Then you should be worried now. But I should also say that there are mitigation measures possible. You could, for example, use secret elliptic curves. You could use additional pre-placed keys. Of course, that's not possible for every application, but for some applications, it's easy option to achieve more security. And the next point is, what's the security lifetime of your information? You have short-lived information. If you're talking about government information, it's 30 years more. Health information, for example, it's your lifetime. What if you use elliptic curves to generate pseudonyms? So these are different situations. And if you ask me how long can we safely use ECC, for some of these applications, the number may be negative at the moment. But then you have other factors. So what's the value of your information? Is it a €5 information that you're protecting? Or is it really valuable? So the probabilities that someone might attack you are quite different. Each user, I think, should do his own risk assessment and find out what these numbers mean for him. But it's really not easy to come up with numbers. One should also, I think we have to accept that there are applications where you just, that are using elliptic curves and where you cannot change them, right? If you have long-lived products that were designed with one built-in elliptic curves, you will see the situation. This may also be the case for IoT devices also that are quite cheap and that don't give you the option to update. Having said these things, I think it's quite important to start the migration to post-quantum cryptography now, and that does not just mean change algorithms. It means you have to change protocols. And our approach is we want to have hybrid protocols so that you can use post-quantum and traditional cryptography together, maybe in the future post-quantum and post-quantum, or post-quantum and QKD. And the overall goal is cryptographic agility, so that in the future updates may become much easier than today. And of course, this is with the understanding that for some products, agility will not be possible because customers don't want to pay the price. We need that, think that industry needs guidance now, and we very much appreciate the NIST process to find post-quantum algorithms. But we also found out that industry needs guidance now, and that's why we have selected two algorithms, Frodo and McAleese, and are recommending them already today in hybrid mode. So we took the, I think, two most conservative choices. The idea is McAleese is quite old and well understood, and we prefer unstructured lattices to structured lattices. That means, we believe if Frodo is broken, then all the other lattice-based schemes in the NIST process will also be broken. And we have chosen something from the NIST process before it's finished, but of course we strongly support the process. In the future, the plan is to add more algorithms to our recommendations as standards evolve. So that's it from me.
Thank you very much, Manfred, for your nice opening remarks. We would like to also, Sam, could you please share your thoughts with us? Thank you.
Yeah. So the main thing that I would like people to take away is when you're trying to interpret on your own what is the progress of quantum computing, and you look at a paper that says it needs 2,000 qubits to run Shor's algorithm on ECC. And then you look at the news and you see Google has this 53 qubit machine, you might think, well, that's not a very big difference. But the Google qubits are not good enough to run Shor's algorithm. Even if you had 2,000 of them, they just couldn't do it because they can only do about 20 gates in a row, and Shor's algorithm needs about 100 million to a billion gates in a row. And so, as Michele said, we need logical qubits, so we need fault tolerance and error correction. So when you do the overheads, you account for the number of these physical qubits, like the ones we see today, that you would need to produce a logical qubit. The overhead is factors of several thousand, and we really need something more like 1 million to 10 million qubits. And qubits that are better than what we have today, better networked, and all of that. So that's a much larger factor. That's 14 doublings, about 14 to 17 doublings from where we are today. So if we take a sort of very naive extrapolation, we say that qubit count doubles every 18 months, the same as classical transistor count. We assume that all the issues, the fidelity gets better, the qubits get good enough to put them in an error correcting code. Then we would imagine from this sort of estimation, Shor's algorithm will break ECC around 2043. So this is why I think I'm a little bit more pessimistic than Michele, and I think perhaps that'll make a livelier panel. And I should say that this estimate, of course, I would put 2043 as my median estimate with an enormous variance. There's so many technological hurdles, and there's also all sorts of unforeseen technological developments. So maybe there will be a lot of troubles because you can't put 10 million qubits in a single super cold refrigerator. So you need a different technology or some sort of quantum networking. And so we might slow down when we have to fix those issues, but we might also have improvements if we come up with better quantum algorithms or some different approach. And on top of all that, I think, as has been mentioned, there's sort of a, even if I think that the median estimate is 2043, what kind of risk are you taking? That's different than don't switch until 2043, or even don't switch until your data needs to be safe by that point, because there's a risk that the time is much sooner. And that's me.
Okay, thank you very much, Sam, for your opening remarks. You were going to say something, Michele? Go ahead.
Should we discuss, or before we move on to the next question? I just wanted to comment. So, I personally give a 20% chance that it takes 20 or more years. And I think Sam's suggesting 23 years. So it's certainly possible. Just like Nate Silver says, Trump might win the election, even though his odds are much less than a half. I guess the only aspect of that I would, the part of the argument I guess I would look more closely at is the doubling every 18 months. Because that's really sort of like a Moore's law type scaling, which I think will eventually kick in once we kind of because that's more about miniaturization, right? You have something, it's established, and now you're going to keep making it smaller and smaller. We don't need to make the first quantum computer terribly small. So I think we can probably, once it works, like the push hasn't been, how can we make them smaller? Nobody's been trying to, to first order, the challenge hasn't been to make it smaller or even bigger. It's been to get it to work, right? And once it works, I expect at some point then they could probably pretty rapidly scale it before you start hitting the usual hurdles of going for, and you will hit a hurdle. Like you can't cram the number of physical qubits Sam is talking about on existing platforms. So there'll have to be a lot of work done. Bigger fridges, bigger something, and these are all very non-trivial engineering challenges. So it partly depends also on how many resources and how many people are trying and so on. I mean, it's a valid argument, a valid approach. But I think the part of that where, but I take a little different approach or give a higher probability, that is one possible trajectory in my analysis. But I think the trajectory that we can scale up to a reasonable number a little faster than just doubling every 18 months is why I think, but at some point I do think it will be that kind of scaling. But I think we'll have a bigger head start than just one logical qubit before that steady scaling kicks in.
Thank you very much for your comments, Michele and Sam. It is very interesting. I'm very excited about all these questions, and actually the audience is the same, is in the same tune because they are asking us a lot of questions. So I will start selecting some of them. Ben Smith is asking, it is clear that you wouldn't want to have an easy root certificate in the quantum era. But to what extent might different conventional ECC constructions remain an option for short-term ephemeral security? I don't know who wants to answer this question. So the question is, you wouldn't want to have an easy root certificate in the quantum era, but to what extent might different conventional ECC constructions remain an option for short-term ephemeral security? I guess when the large-scale quantum computers arrive. So I don't know, Manfred, do you want to answer this question maybe?
At least I can try. Obviously, you don't want elliptic curves for root certificates in the future. The question is, do you want to replace elliptic curves in the future one-to-one with post-quantum algorithms, or do you want to do something similar, for example, also using Merkle signatures in PKIs? Yeah, so it's now I think the time to think about also the structure of future PKIs. We believe that we should support hybrid things like hybrid certificates, and it's now to make the standards. And of course, if you're protecting something very short-lived and maybe not highest value, I can imagine that you use elliptic curves for some more years to come. And you have also the option to just use higher bit numbers. Well, I'm not proposing to use higher bit numbers, but it would be one of the options that are out there.
Okay, thank you very much. I have a question about the last remarks by Michele and Sam. This is a question by Dan Bernstein. He's asking us a question about the various estimates, 2030, 2043. Are these estimates for the public demonstration of 256-bit elliptic curve discrete logs, or estimates for when large-scale adversaries will be able to do this? I don't know who wants to answer this question.
it's a good question. Up until now, I've been mostly treating those as roughly the same within 2 years. But I was, thinking of anyone. But it is a good question. I think we're going to reach a point where we just don't know, and we need to stop asking the question because we've already migrated. It's a good question, but it will start to diverge, and they'll just, right now, again, I give maybe a two-ish year head start, to what we don't know. But after, it's very soon, that's just going to increase that uncertainty, and it will be 5 years potentially with high variance. So it'll be very hard to estimate that. It's already becoming hard. But I guess wonder what Sam thinks.
I guess that would sort of depend on what is the landscape of quantum computers in 25 years, who has them, and why are they building them. I guess sort of what I'm thinking is, just if we're only extrapolating qubit counts today, then again, that doesn't really sort of settle who's going to keep doubling them. And like Michele said, there's this miniaturization issue. So one could imagine that the amount of qubits that maybe are profitable is sort of scaling in some Moore's law type way, because you can only miniaturize it into your fridge, and any bigger it wouldn't be worth it. But maybe an adversary says, well, the technology is good enough, if we just throw a ton of money at it, we could take this technology and build it to a certain point. So that could change the estimate, but again, sort of my number, the variance is so wide at that point, I don't think I could reasonably say whether it would be a large-scale adversary or a public demonstration.
Okay, thank you very much. So we move to the next question. We do have many questions, so the audience is quite excited. And let me ask this question by Chloe Martindale. She is questioning, how independent are the number of gates and the number of qubits? Can we deduce anything about the precise number of qubits needed from the PQ Crypto 2020 paper? Or is that a separate question? She's asking. So basically, she's asking how independent are the number of gates and the number of qubits. So I will jump in and. I think yes, Sam. I think that she's talking about the PQ Crypto 2020 paper by Hanner, Jakes, Nerik, Rotterler, and Soken.
So there's a loose relation between that. So we say in our paper the number of logical qubits, and so then the question is, how many physical qubits does that imply? And for a surface code, for example, the ratio will be roughly proportional to the square of the log of the number of qubits times the total circuit depth. But that changes a bit because to produce T-gates, you need these so-called magic state factories, which require extra qubits and sort of extra space. So the relationship is more complicated than that. And if you want to do it properly, you would write some code to sort of go through all of this. You would have to figure out some sort of physical layout to arrange these states and these all of the gates. So there is no precise relationship, or there is a precise relationship, but it's not easy to describe. I'd say basically my own sort of estimate on this is I take the number from the Gidney and Ekera paper, where they say it's a factor of about 3,000, and simply multiply that by the number of logical qubits, because it's about the same number of T-gates and circuit depth. But this is an imprecise estimate.
Okay, thank you very much. So we now have a question by Nikita Snetkov. He's asking, why do you think NSA, in their perspective on PQC, ignores isogeny, multivariate, code-based crypto, and only focus on lattice and hash-based crypto? I guess he's referring to the results of the third round in the NIST contest. I don't know Which one of you would like to answer that question?
Well, I don't think they ignored that. I mean, there's the reserve, whatever, the alternate list includes the isogenies. So I think they explained why. Just give it more time to be studied and developed.
Okay.
I think it's important. I think it's very critical to keep that biodiversity in our toolkits, so to speak. So I think I'm a big fan of it, of course, but I mean I'm fine with going with the more reliable, the ones that have been around longer, and in some sense are considered more ready for showtime as the short, list to initially, because this is not a competition. They're not going to pick one and then stop. Like they've been very clear about that, I think. So these alternatives, I definitely think should continue to be studied and eventually standardized.
Okay, thank you very much, Michele. I have here a very interesting question by Dan Brown. He's asking us, how do we compare the chance of breaking whatever PQC algorithm used to the chance of building QC to break ECC? So how could you compare these post-quantum cryptographic schemes, the possibility that they can get broken, against the possibility of building a quantum computer to break ECC? Is the amount of effort spent on these two tasks comparable at all? This is his question.
So I missed the first part.
How do you compare? He's asking this. How do we compare the chance of breaking whatever PQC algorithm used to the chance of building quantum computer to break ECC? Are these two events comparable?
So I could give you my personal views on the two probabilities, and then you can just directly compare them. So I've already given you my own personal estimates, and we have a histogram of other people's estimates of quantum cryptanalysis of ECC. And then for my own sort of estimate of the chance of cryptanalyzing whatever is standardized in 2023-24 is in a 10-year period, in the subsequent 10 years, at close to 10% and going down, right? So you have this shifting 10-year period. The probability of being broken in the subsequent 10 years will start at 10% and eventually go down to something close to 1%, which is roughly what I think is a chance that ECC gets cryptanalyzed in a 10-year period. And that's my own personal estimate. So you can see the crossover points there.
Yeah, I think you cannot compare these two questions really, because for quantum computers you know what you need, and you are doing, I would say, engineering, and you have to build something. On the other side, if you want to attack an algorithm, you need one genius with a good idea and it's broken, right? And you may want to introduce something like Moore's law for mathematical progress, but that might give you an idea when you get something better, but you don't know. And for elliptic curves, I mean, at the moment you have Pollard's algorithm, more or less, and what would be the next step? Something like the number field sieve, so that you get something sub-exponential. It's one idea. It's like a black swan event. You cannot model them.
I see.
Yeah, great point. I mean, I was sort of giving mean values, but it's very different types of estimates in terms of variance and how we can sort of track and estimate. And so, really good point.
If I can just jump in, even though the methods one would need to estimate the two events are very different. They are still risks to ECC, and kind of if you want to have your secret safe, it doesn't matter which risky event happens, and you kind of still need to estimate which one's going to happen. And I agree, I have no idea how one estimates what algorithmic progress is going to be made. But it can't sort of be discounted just because it's sort of it's easier to estimate, you know, how quantum computers must progress to break ECC.
Okay, thank you very much. I have now a question specifically for Manfred. This question comes from Caroline Barner. She's asking, if memory footprint is a prime concern, so classic MATLIS and Frodo-Chem are not an option, which post-quantum key exchange would you choose for hybrid operation?
So actually, we know these problems. We know that some applications are not possible with MATLIS, but others are. And what we want to offer is a variety of options to industry, more or less. For government applications, we are certainly going for unstructured lattices, and at least for the high classification rates, and for the lower ones, we will see over time.
I see. Do you want to add anything about this, Michele, or maybe Sam? No. Okay, so let's move to the next question by Lawrence Pani. He's asking specifically to Michele. In the survey that you mentioned, are the consulted experts anonymized? He says, I see a general risk of people giving overly optimistic estimates to secure funding.
So the list of respondents is not anonymous. Who answered what is anonymous, unless they explicitly. I mean, the statistical numbers. I don't think we say who answered what, but then there's a long list of other questions to really interesting material to understand. What their view, why they're thinking what they're thinking, and so on. And many of those are not anonymized. I mean, I think that cynical view is not justified. I mean, I wouldn't, certainly not deliberately. None of the people we've asked, I think, would play that game. And we deliberately went to people who are not in the business of giving these estimates, but whose opinions we think are valuable, right? So they weren't, they didn't proactively come to us and say, here's what I think. We went to them. So I don't think there's a high risk of that. I think there's equal risk. I think there's even more risk, and again, certainly not deliberate in terms of natural human biases. I think there's also, there's, and you'll see it in the commentary, they're very concerned about the hyping, right, and setting up this expectation that isn't met. So I think there's probably more risk of the other end of the spectrum, but I don't know. So we're just going to report, and we do briefly discuss this issue in the commentary, at least we did last year. But I don't think that, these are their honest estimates. They might be wrong, but we're looking at 44 serious distinguished scientists with a diverse group of people all around the world. I'd be worried if we asked the same kind of person, right? 55-year-old white male experimentalists in North America. What do you all think? Because then there's going to be a more correlation. These are valid, valid views, very meaningful views. But we've asked people from different stages of their career, from all around the world, working in different and relevant aspects. And there's a lot of variance, but there's still some common patterns as well. So it's a fair concern. But we obviously thought about that, and we deliberately asked people who we thought would give their honest views. And you'll see there's a lot of people ticking the, I think this is not going to happen in 20 years box. box as well.
Okay, thank you very much. Manfred, you want to add something? Go ahead, please.
I wanted to add something on this. We have heard similar theories. We were approached by someone who claimed that there's a world conspiracy by physicists to get funding, that they all know that in principle quantum computers are impossible to build. I wouldn't buy this because the funding comes from so diverse agencies and countries and companies. And this would mean that the overseeing bodies in all these organizations would just fall to the same lie, and you would have to organize it worldwide. And that's something I just don't want to believe.
Okay, fair enough. I will just ask one question from about this topic, just to close this topic. Large companies such as Google, Microsoft, and IBM, and also venture capitalists are investing large amounts of money towards building a quantum computer. If there is no major progress, say in the next 5 years, what is the possibility that funding for quantum computing research could decline or even vanish? Is that a possibility? I don't know who wants to answer the question. Okay.
Yeah, I think it's natural that, so first of all, that's not the trend we're seeing, right? Progress continues to be made at a very, very impressive rate. It's slow. I mean, many people are impatient, but, if you listen to what the actual people doing the work have been saying for the last 10, 20 years, they've not promised anything. This hype notion is really not coming from the scientists and the engineers building the devices and so on. So they've really made tremendous progress. So that's not what we're seeing. But the question is, what if we do see that, then yeah, of course, there'll be waning, interest in funding it will reduce. And the amount of reduction will depend on a lot of things. Like, is it slowing down because we've uncovered some really fundamental roadblock? Right? If there starts to get widespread consensus in the scientific community, like, yeah, this is a lot harder than we thought. Like, we always thought it was hard. We always knew we were going to uncover, like when Google made their 72-qubit chip, like almost certainly it was going to uncover all sorts of challenges that they knew would be there, but they didn't know what they were going to be in advance. So we've always expected that. But let's say we uncover something like a really new, better understanding of how these quantum systems work, and suddenly we say, like, yeah, like now we understand why errors will not satisfy the conditions of these fault tolerance, theorems, right? That kind of showstopper would justifiably, reduce the amount of funding and interest in quantum computing. But again, we're not seeing that, and if we see it, then exciting, advance in physics, but would definitely slow down quantum computing if we found what we believe to be some fundamental obstacle. I think that's a low possibility event. It's a small part of that 20% probability I talked about earlier. But if it's something in between where it's kind of, they don't get a logical qubit by 2023, it's looking more like 2026. I think it'll slow things down a bit, but not really, right? If we're still getting close to that part where we're going to achieve a logical qubit, because we know once we achieve that, then the risks start going down a lot, right? The technology risk drops a lot. Because then we would have demonstrated that you can actually achieve a scale fault-tolerant qubit, and then how fast and how well can we scale it? Or is there another platform? It'll be like the 4-minute mile, right? Once one platform does it, I don't think it'll be too long after another might do that. So even if that one starts to take a long time to scale, longer than we'd hoped, there'll be another one, a better. Like, the physicists aren't going to retire once they we didn't stop after ENIAC, right? We developed better and better platforms. So one of these is going to cross the finish line for being, commercially useful, cryptographically relevant and commercially useful. So I think it'd be a bizarre time to pull the plug as we're inching closer to really achieving that very critical milestone of a fault-tolerant qubit. So again, unless this slowdown in the process of the slowdown, we really uncover a fundamental reason why we're not going to achieve fault tolerance. And if it's really just it's taking a bit longer than we thought. Again, all our probability estimates, we don't rule out the possibility that it takes 10 years to achieve fault tolerance, right? But if there's still objective progress, then I don't think there's not going to be a quantum winter, maybe a quantum autumn, but I'm not so sure about that either. So it really depends on the severity of this, slowdown in progress. It really largely depends on and the nature of it.
Okay, thank you very much. Yes, Manfred. I just want to make. Okay, go ahead, Manfred. Go ahead.
I just wanted to add one aspect to this. We are now talking about cryptographically relevant quantum computers. But for chemistry and other applications, you may need smaller quantum computers. So it's quite probably that you will see quantum computers that you can use to do something useful in the nearer future. And this would give companies an incentive to invest further. And by the way, they are not only making money with building quantum computers, but also with the patents that they get during this process. So it's not really lost money. Yeah, there may be a plateau. Yeah, so that you reach the chemical industry bound, and then you wait some years. That would be my guess. And after that, you have learned more, and the engineering becomes better, and you start off again.
Okay, fair enough. Thank you, Manfred. Thank you, Michele, for your comprehensive replies. And I would like to let you know that we have tons of questions, literally tons of questions. It is literally impossible to address all of them. So I encourage you, to all three of you, to please reply and answer these questions in the Zulip. I have one question by Andrew Sutherland. He's asking us, I'd be curious to know what the panelists have to say about the availability of quantum computers from a constructive perspective. When do you think quantum computers will be available as a practical tool for research in number theory? How confident are you that this will eventually happen? He is asking us this question. It's an interesting question. What do you think about it?
Well, in some sense, they already are, right? I mean, IBM has its platform available. AWS has already introduced an interface which plugs into many platforms. And so they're all pushing to some sort of online or cloud access to their existing platforms. Are they useful for number theory? Probably not yet. You can study lots of things. You can study many body physics, maybe, and chemistry. So they're online. They're already trying to sell services, largely to researchers and to companies doing R&D. So I don't think it's part of their business plan to not make it accessible once it's actually useful, as it becomes more and more useful. So I don't see the only reason it would happen is if we didn't get post-quantum cryptography and potentially also QKD, into our critical systems soon enough, which would have been a human, market failure, human failure if we don't protect our digital systems in time, so that we're actually literally discussing whether to stop the positive application of these platforms. So I hope that doesn't happen. That would be a really sad, yet another sad situation for humanity. But otherwise, they're already trying very hard to get people who want to use it access to their platforms. And the challenge is they're the pre-fault tolerance. This is the NISQ era, so you have to deal with all the noise, and it's a relatively small number of qubits, so you can't do most of these number theory algorithms you'd be interested in.
Got it. Okay, Michele, I have a question for you because I know that you may need to leave soon. So this is the question that I have. Just a second. Here. Michele, your previous estimate is that RSA 2048 had a 1/7 chance of being breaking via Shor's algorithm by 2026. But you now have revisited it down to 1%. What were the developments in quantum computing that changed your mind? Or was it just a lack of black swan events that accelerate progress?
So, the way I look at it, in 2015, I gave a 1 in 7 chance of it happening in 11 years, right? And then 2 years later, a 1 in 6 chance of 10 years. And 2 years after that, a 1 in 5 chance in 10 years, right? So the Russian roulette probability is monotonically decreasing. So, because I think I've only seen, there's ups and downs, but the average state of affairs has generally been increasing the likelihood that this is going to happen. Right, and so it's generally been progress. There haven't been any, the negative discoveries were somewhat, to some extent, expected. Again, didn't know exactly where, but it wasn't surprising that these chips have noise that didn't exist or had effects that we didn't see in the 9-qubit one-dimensional chips. Of course, we're going to see different noise and when we integrate them into 2-dimensional chips. So the probability within a 10-year time slice has monotonically gone up. I don't know if I said down earlier, but the probability. So, and this is how this is how probabilities work, right? These sort of stochastic. I mean, I'm modeling it. It's not it's not independent. The probability keeps going. So it's like Russian roulette, where the chance of a bullet keeps going up every year, right? So nothing terribly shocking happened, other than, again, that's how probabilities work, right? A 1 in 6, 1 in 7 chance in 11 years. That means the 2026 probability has a 1 in 7 chance of eventually going to 0, and 1 in 7 chance of climbing up to 1, and a 6 in 7 chance of going to 0. Right? So that's probably what's going to happen. Is it won't happen in 2026. So I got whatever my 2025 odds. Or, actually, this is in 2019. So my 2024 odds, I had it about 1%. But that's right. But that's sort of what you expect to happen. I think if you want to trend progress in the field, what indicates that is the fact that the 10-year probabilities have continued to climb up.
Okay, thank you very much for your answer. I would like to encourage everyone to go to the social break that we will have on Wonder, because clearly it would be impossible to address all the questions, and people are really excited, our audience, about this topic, and they keep asking questions. So please don't forget that we have this social event in Wonder, and also that we will have another panel, a fourth panel coming about psych. So I have one more question by Gregor Bransky. He's asking us the following. He says, given that ECC is used in signatures as well, how do you address the issue that quantum computers will be able to not only retroactively decipher messages, but also produce faked signatures, as those are allowed to forge documents and such? How could this be a problem, he's saying? He's asking. I don't know, maybe Manfred wants to answer this question. Can quantum computers?
I can try. One way would be to, at the moment you expect that there are no quantum computers and that your system is secure. So this gives you the possibility to re-sign your messages or oversign the received signatures. And then you are sure that you have checked them today, and today it's secure. And the security then relies on the new scheme.
Okay, thank you very much. Now Fabio Campos is asking us, why shouldn't we use post-quantum RSA? Maybe Sam wants to answer this question?
I guess there's the obvious answer, which is the performance. And so I think it is, at all points when we're using crypto, we're making some sort of cost benefit, and we're always, there's some risk that this scheme is broken, but the benefit is, it's very fast. It works well. Why not use much larger schemes in any context? And I think with PQRSA, it's clearly unfavorable. It's way too slow. So.
Okay, thank you very much, Sam. And I have one question by Stephen Galbraith. He's asking the following to you, Sam. He says, if I'm reading the PQ Crypto 2020 paper by Hanner, Jakes, Nerik, Roteler, and Sulken correctly, the smallest Toffoli gate count for solving a 256-bit ECTLP instance is more than 10 to the 9 gates. According to Wikipedia, the Intel i7 Skylake chip in my laptop has around 10 to the 9 transistors. This is the culmination of 70 years of progress in semiconductors. Is this a fair comparison? Could I safely conclude that we are many decades from having the technology to build a quantum computer with 10 to the 9 Toffoli gates?
Yeah, so Dan Bernstein gave a great answer, so I'm basically going to almost repeat that. But the thing to remember is, in quantum computing, the gates are not a physical object that's on a chip or something. It's sort of this abstraction of some process that changes the state of a qubit. And so in, say, a superconducting chip, you're shooting lasers, and so a particular laser pulse is a gate. And on a error-corrected surface code, it's a certain pattern of measurements that produces a gate. And so when we say that there are 10 to the 9 gates, we mean you're doing some operation 10 to the 9 times. And so you don't need to produce 10 to the 9 manufactured components. You need to produce some number for the qubits, and then you need to put in the energy or computational work to do all of that. So as he sort of says in the follow-up, why didn't we simply call them Toffoli operations or T operations? And it's just, the standard is gates, but operations is more clear.
Okay, thank you very much, Sam, for your answer. This has been a wonderful, really wonderful panel, but we need to end it. I would like to end it with 2 more questions, one for Manfred and one for Sam. For Manfred, I have this question. This question about P256 versus P384 elliptic curves. The latest recommendations from NSA are to use P384. Do you have any reckoning of why they are recommending P384 over P256?
Well, actually, I don't know what NSA thinks, but I can tell you how our thinking is, because we have a similar recommendation. And the idea is, if you have the P256 curves, the security level is 128 bit, and we think that security should be higher, right? Especially when you're thinking about quantum computers, when we are now giving the recommendation to use AES 256, and using AES 256 together with curve 256 would reduce the security level to 128 bits, and that's I would say not very optimal.
Thank you very much, Manfred. Okay, and my last question for Sam, an obvious question that everybody is asking. Which one will be broken first, in your opinion, RSA or ECC?
So a more narrow question is, which one will Shor's algorithm break first? And I think I would say ECC with some confidence, because it seems to be easier. Which scheme will be broken means I have to account for, say, algorithmic advances. And I'm much less sure there, because factoring seems like a problem that has had so much more progress, and it seems more tractable than elliptic curve discrete logs. And so then it's a question of, will there be some sort of factoring breakthrough before quantum computers can break either one? And I am not the expert to answer that, but certainly that's looms as a possibility in my mind.
Thank you very much, Sam. Thank you very much, Manfred. Maybe you want to have some closing remarks? Any one of you?
So first of all, it was a pleasure to be on the panel. I think we discussed very interesting questions, and maybe the takeaway message is we know that something has to happen, but we don't know when it will happen. So when the quantum computer will be there. But we know it's time to act now.
Thank you very much, Manfred. Sam, any closing remarks that you may have?
Yeah, I guess my main closing remark is that there are a lot of hurdles we have to get through for quantum computers to be a cryptographic threat. But at the same time, we should also be aware that there's some risk that some of those hurdles are actually much easier than we expect. And so sort of our best guess on when quantum computers break crypto is not necessarily what we should be aiming to secure against.
Thank you very much to both of you. And thank you to all the audience for being with us. It has been a wonderful panel, and there is more in our social coffee break event. So please do enter in Wonder and keep the discussion going. Thank you very much to all of you. Thank you, Manfred. Thank you, Sam. Bye.